let's start week 8 lecture, and which is the introduction to the t-test, and it is chapter 7 in the 6th edition of Aaron and Aaron, and chapter 8 up to 6th edition. Now, the first computer test will be held in week 8, and if for any reasons you missed your test on your own computer lab time, please contact other tutors for other lab times prior to their tute, and if they said it's okay, you can see it for the test in their session. Now, the computer test, because it is its weight is 15%. The only way that you can sit for the test later than week 8 to submit a special consideration. Now, you have had the sample computer test, and if you have gone through that one, it's not a very difficult test. You only have got the descriptive, the analyze, descriptive, and then explore that you have to be worried about, a scatter plot. And if you're okay with that, please sit on your own time. And there are, in the other hand, there are 19 computer labs running on weekly basis for this subject. So if you missed your class time, or you knew that you were going to miss your class time, please contact the tutor for the other time and get the permission to sit for the test in the other tutor's time. And because we are using virtual desktop, your best bet would be to attend your own computer lab. You should know that you only get one chance. When you click on the computer test, then you have to do the test. And if you prefer to do the test other than your computer lab time, you can do it, but you're running your own risk that if something goes wrong, the tutor is not there to help you. But you cannot email me later and say that I wanted to do it, for example, 9 o'clock at night time, and then the internet got cut off, so I didn't do the test. And can I do it again? That would not happen, because as you know, we have got about 500 students, and that makes life really difficult to be able to accommodate that. I know it is hard doing online, but believe me, teaching online is harder. Now, let's talk about the objectives for this week. We are talking about the t-distribution, its purpose, and determining appropriate cutoff values using t-tables. Now, we get to figure the t-test for a single sample and a known population mean, and figure the t-test for dependent means, which we call it paired t-test, or paired for dependent means, or repeated measure t-test. And then interpret the results from t-test for dependent means as reported in the psychology research articles. And you should be able to calculate the 95% confidence interval using t-tables. And by now you should know how to calculate 95% confidence interval for the z-scores when the population standard deviation is known. Now, what would be the assumptions for t-test, and what would be the effect size when you have got the t-distribution or t-test? Again, this is the same table that I have shown you before, and remember, we have got 3 different distributions. One is the population of the individual scores distribution. The mean, we call it as mu, or in Aaron and Aaron it says population M. Then we have got sample distribution. When we take a sample of size n, then the mean would be represented as either m or x bar. Both of them are correct. But then we have got the third distribution that we talked about, central limit theorem. And it would be, if you remember, I said, imagine that from the population of individual scores, we take a sample of size, let's say 20. And then imagine that you take this sample thousands of times and with replacement from the population and get thousands of samples of size 20, and you get the X bars. And then the distribution of means the distribution of those X bars. But we know that in reality, we don't take thousands of samples. We only take one sample of size 20 and then draw conclusion about the whole population of samples of size 20, let's say. Then variance and the standard deviation, I just showed you the characters we used for the three different distributions in that table. So far, we have been concentrating on hypothesis testing for samples from a normal population with the known variances. So remember, known variance. But a more general situation we might encounter is where we have samples from a controlled population and from some other population, and we wish to compare population means. So what do we mean by that? The control population is just a general population, and then the other population, we mean that population of our interest, for example, the treatment group, or for example, in the further examples, you will see that the general population of students, La Trobe University students, would be the control group, some measurement for those, and then we are interested in the variable from the population of psych students. So nothing is known about the population from which the samples were taken, except perhaps that the underlying population distribution was normal. In particular, we do not know the variance of the population involved. So, and up to now, in order to make inferences about the population mean, we conducted hypothesis testing using Z-score. So, we calculated the sample mean, and we said that sample mean is represented by either M or X bar. Both are fine, whichever you're more comfortable with. Calculate the standard deviation of the sample means, which we call it a standard error. And to determine how much difference is reasonable to expect between sample mean and the population mean. Then we, in order to quantify our inference about the population mean, we calculate the Z-score. So we say the sample mean, M or X bar, minus the population mean, divided by the standard deviation of the means, which we call it a standard error, and it was sigma over root n. Remember, for Z test, sigma, the population standard deviation, should be known if we have got a sample size of n. In that situation, we use the normal table to find the critical region for the hypothesis test. In order to use Z-score, the population variance or standard deviation should be known. Remember that. When the population variance or standard deviation is not known, we can use the sample standard deviation. And you know it from week 2, how to calculate the sample standard deviation from that formula that we went through. And in that case, then when the population standard deviation is not known and we are using the sample standard deviation, then we have to use T statistic to approximate your Z-score. So we don't use Z-score, we use T-score. So we call it T-test for single sample, which is the hypothesis testing with a single sample in a population for which the mean is known but the variance is not known. And it works exactly the same as what you learned in week 6, except that we estimate the population variance. Instead of using sigma, we use S. Yeah, the sample variance and sample standard deviation. After we use that one, then we have the estimated standard error. You know, the standard error when the population standard deviation was known was sigma over square root of n. But when we don't have the population standard deviation, the estimated standard error would be S over root n. So for the figuring out the cutoff score, we use T table instead of Z table. So t-test for a single sample is used to compare the mean of a sample with a population for which the mean is known but the variance is unknown. Remember that. And unlike previous methods of Z, one must now estimate the population variance from the scores in the sample. So it means that you calculate the sample variance of sample standard deviation. And as a sample represents its population, its variance is representative of the population variance. And as mentioned in week 2, variance of the sample is smaller than the variance of the population. Because in the population you might have a score very, very small or a score very, very large because it's from the population. But in the sample, you might not cover that very, very large score or very, very small score in your random sample. Therefore, you can see that when you calculate the variance of the sample, it would be bias estimator of the population variance. And let's say that if we say SS would be the sum of the square deviations from the mean in the sample, then you would have the degrees of freedom. If you divide the SS, the sum of the square deviations from the mean. So do you remember, if we have got this data set, each value we take the mean from it, square it, add them all up together, that becomes sum of the square deviations. Then we divide that sum of the square deviation, if you remember, by n minus 1. You remember a lot of you asked me, why is it that you divide by n minus 1? And I told you that because if you divide by n to get the average distance of the scores from the mean, then because sample is not covering all the let's say outliers or larger values and smaller values, therefore in order to stop the bias estimate of this average distance of scores from the mean, we have to divide by n minus 1. This n minus 1 is called degrees of freedom. And it has this name because the number of scores in a sample that are free to vary if you know the mean and all the individual numbers but only one, you can figure that final number. That's why it is called degrees of freedom. And then for one sample t-test, degrees of freedom is sample size minus 1 and minus 1. And then these two formulas are exactly the same. The only thing is here we say that the S squared that you know already to calculate the variance of the sample, the sum of the square, the deviations is divided by sample size minus 1, which is called df, the degrees of freedom. Now, the greater the value of df, or the degrees of freedom for a sample, the better the sample standard deviation squared, or the sample variance, represents the population variance. And the better the t-statistic approximates the z-score. If you select all the possible samples of a particular size m and compute the z-score for each sample mean, then the entire set of z-scores will form a z-score distribution. Alright? Now, in the same way, if you can compute the t-statistic for every sample in the population, and the entire set of t-values would form the t-distribution. Now, t-distribution is the same as the normal distribution. It is bell-shaped curve, it is unimodal, and it is symmetrical. The only thing is the dotted line is the t-distribution as compared with the normal curve. You can see that there are more scores in the extremes for the t-distribution. So it has got a heavier tail, we call it. And then we have to, the sample mean has to be slightly more extreme to be significant with the t-distribution than with a normal curve. So when the population standard deviation is not known, we are using one sample t-test for the ones, if we had only one sample, and the comparison distribution would be a t-distribution. So we first need to figure the variance of the distribution of means from the sample variance. So when you have got the set of numbers, first you get the variance of that sample by taking the mean from each score, square it, add them all up together, and divide by sample size minus 1 in order to get the variance for the sample. Then the estimated standard error, which would be the standard deviation of the sample means, or variance of the sample means here, would be the variance of the sample divided by the sample size. So that is the variance for the sample means. But standard error, which is it's the same as the standard deviation of the sample means, is the square root of the variance of the means, which would be the square root of this one. So becomes S divided by square root of n. Okay, so t-test for the single sample, we have to determine the cutoff sample score for rejecting the null hypothesis using t-tables. And in my lesson in week 8, I have shown you the t-table and how you use it. And then to get your cutoff scores for the different significance levels. Then figure sample means score on the t-distribution. So your t-score would be the mean, exactly like z-score, but this time the sample mean minus population mean divided by the standard error, which is the standard deviation of the sample means, but instead of sigma you use S. So you can see that how similar it is when the population standard deviation is known. It is Z and it is x bar minus mu over sigma over root n. When it is the population standard deviation is not known, it is T and it is again x bar minus mu divided by S, the sample standard deviation, divided by square root of n. So this there are two examples. I want to talk about them in this lecture, but writing it and demonstrating it like pen and paper, I have already made mini videos for you in the lesson in week 8 that you should go for in the lectures, mini lectures in the lesson, and I call them 8.1, 8.2, 8.3, 8.4. Please go through them to understand exactly how you should do the one sample t-test. So just to show you an example, two examples of how would the question be, where you get the hints in the example that you would know, oh, this is a one sample t-test, I show you now. So the example here says, suppose it has been stated that in general, students at La Trobe University study an average of 2.5 hours each day outside lectures. You think that students studying psychology study much more than this. All right. So when it says in general 2.5, you say, okay, I know mu is 2.5. Then when it says it is hypothesized that psych students study much more, so you say, oh, so it's a one-tail test. And it is the right tail because we say more. We don't say less. Now, it says you randomly pick 16 students. So you say, okay, my sample size is 16. N is equal to 16. From this course, and ask them how much they each study each day. You discover that these 16 students study an average of 3.2 hours. So my mu is 2.5, my x bar or m is 3.2. With a sample variance of s squared is equal to 0.64 or standard deviation is 0.8. So this is a sample standard deviation. So it already, the question tells you that it is S, not sigma. What should you conclude? Okay, so you had a sample of size 16. The average for that sample, x bar, was 3.2. Then you have the normal distribution with the mean of 2.5 would be the distribution, normal distribution. Your comparison distribution, the mean would be 2.5, but the standard deviation would be the standard deviation of the sample means of x bars, which would be narrower. And your cutoff score should be from t distribution, not z distribution. Okay, so as sigma is not known, we use S to estimate sigma, and therefore we use t distribution instead of z distribution. When we have a sample of size more than 1, the comparison distribution, remember, changes from distribution of population of individuals to the distribution of the sample means. So you have got a standard error. Depending on whether the population standard deviation is known or unknown, the comparison distribution could either be a standard normal with the mean of 0 and standard deviation of 1, or it could be a t distribution with n-1 degrees of freedom. So when the population standard deviation is not known, your comparison distribution is not z distribution anymore. It is t distribution with n-1 degrees of freedom, or sample size -1. And here we had got a sample of size 16. So you can tell me that a sample size of 16 means degrees of freedom of 15. Sample size -1. So my comparison distribution, straight away you say t distribution with 15 degrees of freedom. Now I've gone through all the steps very carefully for you in the lesson, in the mini video lecture. I don't want to repeat myself. Only the very important points is your parameter of interest mu would be the average time that psych students study per day outside lectures. You have got a one-tail test, and the standard error would be sample standard deviation divided by square root of n, and t score, t statistic would be the same as z score when you have got a sample of size n, only instead of sigma, you have got s. And the cutoff score, you look at t tables and look at 5% significance level for 15 degrees of freedom in the table A2 for a one-tail test. These are very important. And try to find the cutoff point, which would be 1.753. You can use ESKI or T-table to get to this cutoff score. And I would like you, please, to go through the lesson in week 8 and then find out yourself from an Aaron and Aaron table in A2, table A2 about this cutoff score. That if you do that, you will learn how to use the T-tables. Then do the same thing. This time you go to normal ZT in ESKI and make the probability 0.05 and find the cutoff score for one-tail test. So the cutoff score is 1.753. Your test statistic is 3.5. So the test statistic T is more extreme than the cutoff score. So it falls into the rejection region. So you have got enough evidence to reject the null hypothesis, because in the null we said there is no difference between the average time that psych students study each day as compared with the general population of La Trobe University students. We reject this one and we conclude that the psych students study more. We have got significant evidence, statistical evidence about this hypothesis test. This is another example. Again, I have done all the calculations by hand in the mini lecture in your lesson link in week 8. Please go through that very carefully. I again talk about the important points. Here it says a particular office task is considered to take on average 60 minutes to complete. The office manager wants to increase productivity. See, it says increase productivity. She is interested in seeing if playing classical music may help. She randomly selects 10 employees, n is equal to 10, and gets them to perform this task. With classical music piped through the office, the time taken by each employee to complete that specific task is recorded as these ones. These are the 10 scores that your sample has got. Now, let's say we wanted to carry out a two-tail test for 10% significance level. Okay, so here the question instructs us to carry out the two-tail test. If it didn't, then because it says the guy wants to increase productivity, it means that we want to make the average time to complete this task be less than 60 minutes to increase productivity. So remember, when you do your alternative hypothesis, think about the direction of your test. Now in here it says carry out the two-tail test, and then it says at 10% significance level. And it says that can you do the 90% confidence interval. So here I have just I say that mu would be the mean time taken to perform the task with the classical music playing. Here we followed from the hint in the question, and we said that, okay, we want a one-tail test with a less than 60. So try to do the two-tail test as from previous slide, then do a one-tail test as the question gives a hint. Do your calculations and then figure out your cutoff score if you have got a one-tailed test or if you have got a two-tailed test, because then it would be a great practice for you to get your look at the t-table, look at the cutoff score, look at p-value, and from the t-table you cannot figure out the exact p-value, but we can say if it is between 0.05 and 0.01, or is it between 0.05 and 0.1. So they are very important points that I would like you to go through that. When you get your t statistic, you have your x bar minus mu divided by standard error, and your x bar from here, your values in here, you have to add them all up and divide by 10 to get your x bar. And then you have to use the formula for calculation of variance to get the sample variance. And then after that, you get the square root of the sample variance to get the standard deviation, and then divided by square root of n to get your standard error of 3.3. And this is all been shown to you in the mini videos in week 8. Now we say that the cutoff score for the one-tailed test, t 9 degrees of freedom, because sample size is 10 minus 1 is 9, for 10% significance level is 1.383. And then we have to make it a negative because it's a left tail, because your alternative hypothesis we say is less than, so it's a left tail. Compare your minus 1.383 with your the cutoff score with your observed test score, which is minus 1.79. And because minus 1.79 is more extreme than the minus 1.38, the cutoff score, it falls into your rejection region. So you say that we have got enough evidence to reject the null hypothesis, and say that the people, the employees that listen to classical music will be more efficient. Now the significance level alpha is equal to 5%. If we want to do this time, the cutoff score for 5% significance level will be minus 1.833 for one-tailed test. Because now we can see that at 5% significance level, then the minus 1.79 is less extreme than the minus 1.833. Therefore, at 5% significance level, we haven't got enough evidence to reject the null. But at 10% significance level, we have enough evidence to reject the null. So these are important points. I know it can be confusing, and that's why here we have got the diagram for when we are doing the here the two-tailed test 10% significance level cutoff scores would be the same as the one-tailed test 5% significance level cutoff score. Now, depending on are you using two-tailed test or one-tailed test, are you using the 5% significance level or 10% significance level, your observed value would be just your calculation that you have done, x bar minus mu over s over root n, which gives you minus 1.79. In here you can see that for two-tailed 10% significance level, your cutoff score is more extreme than the observed value, and you haven't got enough evidence to reject the null hypothesis. But one-tailed test 10% significance level, you can see that your observed value falls into the rejection region. So hopefully I have explained it enough, but you have to draw it yourself and have a look at the recording mini lectures to make sure you don't get too confused with that, because you know that when we do two-tailed test, so 10% significance level, so you have 5% here and 5% here, okay? When you do one-tailed test, 10% significance level, the whole 10% would be the area under the curve, 10%. Therefore, the cutoff score for 10% significance level, one-tailed test, was 1.383. Okay? But the cutoff score for two-tailed test, 10% significance level, would be 1.833. When you do the t-test using SPSS, the sig two-tailed represents the p-value. Now, what was the p-value? P-value was the probability of observing what you have observed, or even more extreme, in the direction of alternative hypothesis. SPSS always gives you the p-value for the two-tailed test. If you wanted to give the p-value for one-tailed test, you have to divide this p-value by 2. That's why your p-value becomes here 0.108 divided by 2, which is 0.054. Now remember, if the p-value is less than significance level, we have got enough evidence to reject the null. But if your observed test score is more extreme than your cutoff score, you have got enough evidence to reject the null hypothesis. So you can see that you have two opposite things that mean the same thing. So cutoff score and observed test statistic and p-value are very fine things that you should understand them very well. In the result of the t-test using SPSS, you get the test statistic that I've done it by hand on the mini lecture in the lesson, and I said it's minus 1.79. Here the SPSS gives you minus 1.785. Degrees of freedom is given to you, p-value is given to you, mean difference, and then you have got the confidence interval. So with your confidence interval, the hypothesized mean for this example was mu is equal to 60. Therefore, when you want to interpret your output for the confidence interval, you have to add 60 to each one of these lower and upper range in order to get your 90% confidence interval for mu. So you can see that here you have got 60 including in the 90% confidence interval. When the null hypothesized mean is included in your confidence interval, you say that you haven't got enough evidence to reject the null hypothesis. Or you can see the p-value is very close to the one-tailed test 5% significance level. It's very close to 0.05. So again, you need more data to be sure about the results. Otherwise, you say, I haven't got enough evidence to reject, significant evidence to reject the null hypothesis. Okay, now there is another test that is very important for you to learn. It's about t-test for dependent means. And it's called repeated measures design within subject design, or pair t-test. And it is when you have got two sets of scores, and then these two sets are dependent on each other. So it compares mean difference scores across pairs of scores against a difference of 0 under the null hypothesis. In other respects, t-test for dependent means is just like a single sample t-test with a population mean of 0. For example, we may administer a test of depression scores before and after individuals take psychotherapy. So, for example, the depression score of Jane was, let's say, 9 before the therapy, and then after the therapy, it became 7. Okay, so these two scores of 9 and 7 are dependent because they both belong to Jane, but it is before something and after something. Or we may administer tests of health status to individuals before and after they take physical activity programs. You may examine an individual's ability to recognize shapes under bright versus dim light. We may measure the alertness of individuals when alone against the alertness score when they are with a friend. You may consider the score on a test of anxiety when individuals are at home and when they are at work. So you can see that all of these, the scores would be dependent. So I show you an example for a paired t-test, and it's very important that you learn this paired t-test prior to we start 2 independent samples t-test in week 9, because then you will have a better understanding that, okay, if I have 2 scores that are dependent on each other, I shouldn't use 2 independent sample t-tests because the scores are dependent. So I have to do a paired t-test. And then, like this example, I go through it. Again, I have gone through a step-by-step of it in the mini lecture. A psychologist interested in the relationship between stress and short-term memory tests 10 subjects prior to and after their exposure to a stressful situation. The question is, test the hypothesis of no difference between stressful and unstressful situations using the data given in here. And use alpha, the significance level, 0.1 or 10%. So, when we want to define the parameter of interest, we say let mu d be the difference between the population averages of short-term memory between pre-stress and post-stress group. Test the null hypothesis, mu d, that difference is 0. So we say there is no difference between pre-stress and post-stress scores. Against alternative hypothesis, we say there is a difference. So we say mu d is not equal to 0. In here, because it says test the hypothesis of no difference, then we know that the alternative hypothesis would be not equal to. And then difference scores can be represented as the population difference as mu d or delta or mu. And this is a two-sided test, as the psychologist was only interested in establishing a difference. There was no prior reason to think the difference was in either direction. Here you have got the difference scores. So what it is, you say, for example, here we have got the difference score 1, 0, 2. It is, you say 12 minus 11 is 1, 14 minus 14 is 0, 10 minus 8 is 2, and you get the difference scores for all of them. And that would be your sample of difference scores. Now, for this sample, then the next thing would be just the steps of one sample t-test. You get the mean, and the mean of the sample, you call it d bar, because it is the mean of the difference scores, and it is here 1.4. And then to get the standard deviation, each score, you take the mean from it, square it, add them all up together and divide by n minus 1. and take the square root of that, and you get the standard deviation of the difference scores as 1.43. Degrees of freedom is the sample size minus 1, and there are 10 difference scores. So your degrees of freedom would be 9 and minus 1. So, and your standard error, which is the standard deviation of the means of the difference scores for sample of size 10, would be standard deviation 1.43 divided by square root of n, which is equal to divided by square root of 10. So standard error is 0.452. Therefore, your test statistic is d bar minus mu d. When the null hypothesis is true, mu d is equal to 0. So it becomes d bar minus 0 divided by standard error, which is the standard deviation of the mean difference scores, and it is 0.452. So you get the test statistic of 3.10. Now, for your cutoff score, you're looking at T with 9 degrees of freedom. And then, depending on your significance level, your cutoff score changes. You go to your T tables and you will see that your cutoff score is 1.833. And we reject the null hypothesis if you have got a value either less than minus 1.833 or greater than 1.833. And here your observed value is 3.10. It's more extreme than 1.833. So you say you have got enough evidence to reject the null hypothesis. If you wanted to do the 90% confidence interval for the mean difference, the estimate of the difference scores was 1.4. Confidence interval formula is the estimate plus minus a factor times the standard error. So the estimate of the difference scores was 1.4. You remember we got the differences, they were here, and the mean for the differences was 1.4. Plus minus, that factor is a T. From the T tables, we look at T with 9 degrees of freedom. If I'm doing here, I'm doing the 90% confidence interval. So it becomes T 9 degrees of freedom for 10% for two-tailed. And that is your cutoff score of 1.833 as well. So that's your factor for the confidence interval. So that factor, which is the T value for this example, because we have got a sample size of 10 with 9 degrees of freedom, and we are doing it the 90% confidence interval, so we look at the T for 0.19 degrees of freedom, two-tailed, is the cutoff score for the two-tailed test for 9 degrees of freedom for T in the T tables. You multiply it by the standard error, which is S over root n, the standard deviation of the difference scores, divided by square root of 10. And you get these two values. So you multiply these two together. Once you add it to 1.4, once you subtract it from 1.4, and you get these two values. Now, the null hypothesis mu d value was 0. We said that mu d is equal to 0. Therefore, you have a look at your confidence interval. If 0 was included in your confidence interval, then you haven't got enough evidence to reject the null hypothesis. If 0 was not included in the confidence interval, like this example, then you say 0 is not included in the 90% confidence interval, so the null hypothesis is rejected. And then we would say something like the paired t-test gave a significant difference between the pre-test and post-test means. p-value is equal to 0.013. We can get the p-value from SPSS analysis, and we conclude there is a relationship between stress and short-term memory. And here I have shown you the SPSS output for 90% confidence interval and two-tailed 10% significance level. Here you have got the mean and sample size and standard deviation for each the pre-test and post-test sets of scores. Then the difference score D bar, you remember it is 1.4. The standard deviation is 1.42. I would like you to just do it by hand yourself and have a look at the mini videos in the lecture. You have to calculate and get the same values. Then your test statistic is 3.096. The lower bound is 0.57 and upper bound is 2.23, and 0 is not included in the 90% confidence interval. Therefore, you reject the null hypothesis. Degrees of freedom is 9, and the p-value, remember, sig two-tailed represents the p-value, and that is 0.013 for the two-tailed test. You have got enough evidence to reject the null hypothesis. So the steps as well for SPSS would be analyze, compare means, and paired sample t-test. You say that let mu d be equal to mu pre minus mu post. Our test is equivalent to testing, mu d is equal to 0 against mu d is not equal to 0. So here p-value is less than 0.1, 10%, because we are doing a 10% significance level. So the assumptions for t-test are: assume that the population of individuals from which the sample was taken is normally distributed. A quick test is to construct a histogram and fit a normal curve so that we can see how closely the distribution of a sample resembles a normal curve. The observations are independent. We achieve this for paired samples by taking the differences. And in practice, one seldom knows if a population is normally distributed. That is okay, because many distributions in nature do approximate a normal curve. The t-test is often still fairly accurate even when this assumption is violated. Now, the effect size for the t-test for dependent means is the mean of the differences scores divided by the estimated standard deviation of the population of individual differences scores. So we mean that divided by sigma. Studies using the t-test for dependent means typically have larger effect sizes and more power than studies with participants divided into two groups. So you can have a higher power if you use a paired t-test. Now, remember that we are using 10% level of significance and a two-tailed test. Thus, for our example, we reject the null hypothesis, and our conclusion is that there is a relationship between stress and short-term memory. Now, with the effect sizes, the small effect is 0.2 for the effect size independent means, medium would be 0.5, and large would be 0.8. Now, how do we do this? As mentioned before, in most situations, the population values are not known. Therefore, we substitute corresponding sample values in their places. The value specified for the null hypothesis mu d is equal to 0. And the sample value is the mean of the differences. And instead of sigma, we use the sample standard deviation of the differences. So, in our example, we put d bar, which is 1.4, minus mu d was 0, and standard deviation of the differences was in here 1.42, 1.43. So effect size, the Cohen's d would be 1.4 divided by 1.43, which is 0.979, which is a large effect. Usually an article reports the value of the T statistic, the degrees of freedom, and the significance level. If we are lucky, there will be a confidence interval to aid in the interpretation with the study is inconclusive. Typically, one sees something like T24 is equal to 2.80, P less than 0.05. If a one-tailed test has been conducted, this usually explicitly stated. Otherwise, you assume a two-tailed test was carried out. Sometimes in the reports, the p-value has 1 star or 2 stars next to it, saying that this is significant. Sometimes more information is given, and the sample mean and its standard error may also be reported. Thanks for that, and this is the lecture for week 8. Thank you.